I'm going to describe a method to solve for electric fields when you have a system of static charges above a grounded plane. And since superposition holds, we can look at the situation for just a single charge. Kelvin introduced this technique, and it's called the method of images. And the solution for the electric field in this situation for the single charge above the grounded plane will show is identical to the solution of a simpler system of just two charges where you have a mirror image of your actual charge of opposite polarity. And we'll show that the solution for the electric fields in the top half here is identical to the solution you would get for the single charge above the grounded plane. Let's begin by looking at our system of our image charges, and let's determine the potential at some point. Let's say this point here. Okay, so that point is a distance r sub 1, say, from the positive charge. So let me define our vector r sub 1, and a distance r sub 2 from our minus q. So r sub 2 is the vector that points from the minus q to our point P at some position r. We can use superposition to find the potential at this point by finding the potential first due to the plus q charge and then the minus q charge. Okay, so the amount of work to bring 1 coulomb of charge from infinity to point P, and assuming point P is at some location little r, is q over 4 pi epsilon sub 0 times the length of vector r sub 1. And the potential at our point P due to our minus q is the amount of work to bring 1 coulomb of charge from infinity to position r with just minus q there is minus q over 4 pi epsilon sub 0 times the distance our point is from our charge minus q, or the length of this vector, just r sub 2. Now, for convenience, let's pick the potential at infinity to be 0. Then the potential at position r is just the sum of these two terms. So the potential will be q over 4 pi epsilon sub 0 times 1 over r1 minus 1 over r2. And then, of course, if we wanted the electric field everywhere, we could just take the gradient of this scalar potential field. If we go to any point on the plane that's midway between our two charges, so for instance this point here, so now this is vector r sub 1, and this is vector r sub 2, then the lengths of r1 and r2 will be the same. So the potential anywhere on that plane is going to be 0. So since the potential of this plane midway between our two charges is 0, we could bring a conductor of negligible thickness, a conducting plane, and slide it into this region between the two charges, and there would be no perturbation to what's going on in terms of our electric fields and our potential fields anywhere. So now let's think about just making this negligible thickness conductor. Let's just give it a tiny thickness, not enough to really disturb our field patterns. If we do that, then we'll have the following situation. So then what would happen would be the electric field lines emanating from the positive charge would terminate on electrons, negative charge on the top part of this plane, conducting plane, and then reemerge from the positive charges on the bottom part of the plane. So now you can think of this infinite conducting plane as a Faraday cage that is isolating the top half of our universe from the bottom half of the universe. So now I could move this negative charge around in the bottom half of the universe and it would not cause any effect on the top half. So you could actually move this negative charge inward and towards the conducting plane. The positive charges then would be attracted and eventually they would all be at the same point in space and you would effectively have this situation. So now we're to our original problem of a positive charge above a grounded conducting plane, and we see that the electric field pattern for this situation is identical to the situation where we remove the conducting plane and put this mirror image charge. So of course below the plane everywhere here the actual potential is ground, but for this part of our two-charge system, we get the exact same field patterns as you would for just a positive charge above a grounded conducting plane. Because superposition holds, then if you have a more complicated arrangement of charge pattern above a grounded conducting plane, you could then remove the conducting plane and put mirror images of all these charge patterns as shown here. So for the positive point charge Q, you put a mirror image charge of the opposite polarity. For this line charge density rho sub L, you put a mirror image of the opposite polarity minus rho sub L. And for a volume charge distribution here of minus rho sub V, you put a mirror image of that charge distribution of the opposite polarity plus rho sub V. So then when you solve this system to get the electric field pattern and the potential pattern everywhere, for the region above the dashed plane, you get the exact same result that is occurring for this collection of charges above a conducting plane. Once you have found the electric field intensity using the method of images, you can find the charge density on the surface of the conductor. You know that the electric flux density field is equal to the dielectric constant times the electric field intensity. In a static situation, you know the electric field intensity and hence the electric flux density is everywhere normal to the surface of the conductor. And if we define a unit normal outward from the conductor, we know that in that direction the electric flux density is equal to the charge density on the surface of the conductor.